Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. We are continuing the topic of drying technology. In the last class, we have discussed the constant rate drying period, how to calculate that, and drying characteristic curve, which is the drying rate versus moisture content, and also the moisture content versus time curve. Okay. Now, today we will continue with this topic. So, drying time calculation for the constant rate period we have done in the previous class for only convection, and today's class we will see the constant rate period for combined conduction, convection and radiation. But before going to that, I would like to remind you the equation that we have developed in yesterday's class. So, for constant rate drying, we have found that if we want to calculate the drying rate, so RC, that is equal to weight of the dry matter divided by the area into integration x2 to x1 dx by dt, or else we can calculate the constant rate drying period or the time required for having the constant rate drying phenomena. So, that will be W d by A into integration x2 to x1 . Okay. So, that we can do. So, here in the constant rate period, if we look into that what will be the effect of different parameter. For example, when we perform the constant rate drying, let us say this is a bed of wet food material and constant rate will prevail till the surface of the moisture will have some surface of the food will have some moisture, that is the free moisture available at the surface, and let us say this is the air which is having the temperature T, humidity H and okay, mass flow rate let us say MA, where the surface is having the temperature Ts, humidity HW or HS. So, what happened that in this case, if the air velocity or air temperature or humidity changes, so this will going to affect the constant rate drying period. For example, we know that the heat is coming from the air to the wet food material by convection, because only we have developed the equation for convection now, but the similar equation can be derived for other heat transfer mechanism. So, if we consider that the amount of heat Q, that is coming from the ambient, coming from the air to the product, so that is equal to Q equal to H, that is convective heat transfer coefficient, into A into T minus Ts or Tw, whatever will be the temperature. Now, this drying will perform in the wet bulb temperature always. Okay. So, this was the case, and then we have seen that H, which is the convective heat transfer coefficient, is related H is related to G, which is nothing but mass velocity that is equal to rho into V. So, rho is the density of the moist and hot gas that is passing over the food product, and V is the velocity. So, naturally if the velocity V increases, that means the heat transfer will increase. Okay. So, if heat transfer increase, then the drying rate will be faster, constant rate RC will be faster, and time required for that drying will reduce. So, this is one case, and if the humidity of this air is increasing. Okay. So, if the humidity increasing, so that means the gradient of moisture transfer will reduce, because the difference between HW minus H will be lowered. So, in that case the RC, that is rate of moisture evaporation, will be reduced. And since we are considering the convective heat transfer coefficient and the moisture transfer from the surface only, the thickness does not cause any direct effect, only it will prolong the time, but does not change the rate of constant rate moisture transfer, okay, or moisture removal during the constant rate drying period. However, if we increase the temperature of the air which is used for the drying phenomena, so if that increases, then the gradient T minus Ts, this will be increasing, okay, and because of that the drying rate will be faster. So, then we can see that all the parameter, that is the air velocity, okay, then air temperature, air humidity, all have effect on the constant rate drying period. Now, in the previous class we have considered that only convective heat transfer is the mechanism by which we are utilizing the heat of the dry and hot air to dry the surface of the food material, okay, by constant rate drying mechanism. Now, if we think about all three modes, okay, that means the conduction, convection and radiation, right. So, if all the three mode are contributing in a case where heat transfer is occurring and drying is taking place from a wet food surface, then how we can calculate the heat transfer rate and the constant rate drying. So, that we will see now. So, let us consider a case where there is a wet solid. Okay. So, let us say this is a food material which is a wet solid material, and that is kept on a metal tray. The food is kept on a metal tray and the block of food is exposed to a hot and dry gas or air stream. Okay. So, air stream is passing over the surface of the wet food material, and also the same air is passing below the metal plate where the food is being kept. Now, what will happen that the convective heat transfer from the air stream to the wet surface of the food will be one mode of heat transfer, and the same air that is passing below the metal plate as well. So, that will also first heat the metal tray, and then from the metal tray heat will be conducted from the bottom side to the upper food material, and also within the food it will be transferred by conduction mechanism. And apart from convection and conduction, if we talk about another method, that is the radiation. So, if we have some source of hot radiating surface, okay, so that is giving radiation heat to the food material. So, radiation heat QR, which is also coming to the surface, and obviously since the it is a radiative source, that TR is much higher than the surface temperature of the food, right. So, now we need to combine all the mechanism of the heat transfer, that is convective, conductive and radiative QC, QK and QR, and all this heat transfer will cause evaporation and drying from the surface. So, first let us see that if we consider the convective heat transfer coefficient, convective heat transfer from the air, hot air to the food surface. So, QC, that is convective heat transfer by convective heat transfer from the air to the food surface will be H, that is convective heat transfer coefficient, into A, that is the area which is exposed to the hot gas, into T minus Ts, where T is the temperature of the air stream or gas and Ts is the temperature of the surface. Okay. Then next we can consider the radiative heat transfer. So, radiative heat transfer, we know that if generally we want to develop the equation of radiative heat transfer. So, it is sigma into epsilon into temperature of the radiative source to the power 4 minus temperature of the surface of the product to the power 4. So, this is the normal expression where sigma is the Boltzmann constant and epsilon is the emissivity of the material. Then Tr to the power 4 minus Ts to the power 4. So, since we want to represent the equation in the similar manner as we did for the convection or conduction, so then we can write this HR as radiative heat transfer coefficient is equal to 5.67 into 10 power minus 8, that is sigma Boltzmann constant, into emissivity into Tr to the power 4 minus Ts to the power 4 divided by Tr minus Ts. Okay. So, convective and radiative heat transfer we have expressed. Now, if we want to express the conductive heat transfer, that is from the bottom this conduction heat is coming through the metal tray to the food material. So, then Qk, that is conduction heat transfer, will be UA into T minus Ts. Now, we have taken U instead of a conductivity, because here we need to take the combined effect of convective heat transfer from the gas to the metal body, then conduction from the metal through the food and also through the food conduction from the bottom to the top surface, that is the Ts, right. So, we have combined all the resistances together and converted to the overall heat transfer coefficient U. So, the expression would be 1 by U, that is equal to 1 by Hc, that is convective heat transfer coefficient. So, to use the similar kind of notation, we can better use here also Hc into A, because here also convective heat transfer we are considering, and from the bottom also it is convective heat transfer. So, 1 by Hc plus this, if we take the length of the metal, the thickness or the height of the metal tray is Lm. So, Lm by Km, Km is the conductivity, thermal conductivity of the heat through this metal body, and Ls, that is the thickness of the food, Ks is the thermal conductivity of the material. So, utilizing this property we can calculate U. Then we can calculate the constant rate by this method, that is constant rate equal to q by A into lambda s. Okay. So, constant rate is actually the amount of moisture removed per unit area per unit time. Okay. So, that will be equal to q, that is the total heat transfer, divided by area into lambda s, that is latent heat of vaporization, and q, since now it is a combination of all three, qc, qr and qk. So, together we can write, taking T minus Ts common, we are getting Hc plus u, and here Hr into Tr minus Ts, right. So, we have taken q by A into lambda s, and q by A is this expression divided by lambda s. Now, this much heat is utilized to evaporate the moisture, so that the humidity changes from H to Hs, because that is the difference. H is the humidity of the entering gas, and Hs is the humidity as the surface, okay, into Mb is the weight of molecular weight of the air, and Ky is the mass transfer coefficient. So, this we have derived in the previous class, that amount of heat transfer will be equal to amount of moisture evaporated into the latent heat of vaporization. So, using this one, now we can generate this expression, that is Hs minus H into lambda s, that we have multiplied here, divided by Hc by Ky into Mb, that is equal to, we have taken Hc common from numerator and use here. So, we have now getting 1 plus u by Hc T minus Ts plus Hr by Hc into Tr minus Ts. Okay. So, this factor H by Ky into Mb, this is called the psychrometric ratio. So, this is how we can develop the relation in case of combined conduction convection radiation. We can develop the expression of the moisture transfer with the heat transfer. Okay. And then we will move on to the falling rate period. Now, when constant rate will end and the falling rate will start, we have discussed a bit of that in the curve of the drying rate versus moisture content. So, we have seen that there is a constant rate, and okay. So, if we express the drying rate with moisture content, so we are getting a constant rate first and then it starts dipping. There may be different pattern. For example, you may find a linear path instantly, okay, and then you may get a second fall in the curve as well. Okay. So, the point when constant rate completes and the falling rate starts. Okay. So, this point we can measure the moisture content, and that is called the critical moisture content Xc. So, this signifies that there is no more free moisture or the layer of moisture available on the surface of the food. So, constant rate drying does not occur at that point, and from this point falling rate drying starts. So, before this falling rate, the controlling or the governing property would be the air velocity or air humidity, temperature, etc., and the drying happen at the wet bulb temperature. Now, the moment drying rate completes and constant rate completes and falling rate starts, so the temperature of the surface of the food, okay. So, temperature of the surface, let us say this was the food and the air is coming over it. So, the surface has started increasing the temperature from the wet bar temperature. So, initially when the constant rate drying happens, the temperature was fixed at the wet bar. Now, whatever heat is transferred from the air to the surface of the product is not utilized for evaporation of the moisture, because the moisture is not available freely at the surface. Therefore, the temperature of the surface starts increasing, temperature of the food starts increasing, and from that point the falling rate starts. Now, the falling rate may continue as proportional to the moisture content. Okay. So, R may be proportional to the moisture content. Okay. It may be linear and may not be linear, but first we will consider the case of linear, okay, and then we can consider a case where it is linear and passing through 0, that means there will be no intercept, okay, in this case. And lastly, we will also see that if the curve is not linear, then how we can define the case of falling rate moisture transfer. Okay. And in this falling rate, the moisture needs to travel from the bottom of the food material to the surface, and in this case the moisture is not uniformly distributed in the food, because of mainly the food is most of the time is not a homogeneous entity, and because of the drying also there may be some change in the structure may happen, some pores may be collapsed. So, somewhere maybe the capillary may build up. So, through the capillary diffusion the moisture can transfer, or somewhere the moisture can be transferred to the vapor because of the vapor diffusion. So, many mechanism can prevail during the falling rate period, and it is very difficult to identify exactly what is the mechanism or how much amount of moisture exactly travel by which mechanism, so that it needs to come from the come from the core of the food to the surface. Okay. And therefore, the rate of moisture removal is reduced in a significant manner. Okay. So, all such happens during the falling rate period. So, basically the rate of drying is decreasing as the free moisture decreases. So, free moisture is actually the moisture which is in excess of the EMC present in the food. So, now what we can do is, for drying time calculation, we can go by different method. One of the method is by graphical interpretation. So, in that what we can do is, we can plot 1 by R versus x, okay, and then we can integrate for the different x that we are getting, I mean the range of x1 to x2, where x1 and x2 both are lower than the critical moisture content Xc, because only below Xc moisture content the falling rate starts. Okay. So, here what will happen, that we can plot it. So, the way we have calculated the constant rate drying period, that is weight of dry matter divided by area into integration x2 to x1 dx by r. Okay. So, the way we have calculated for the constant rate, now the similar thing we have to do for the falling rate as well. So, the area under the plot, that is 1 by r versus dx, that plot. So, x2 to x1, this area of the curve we can calculate and then multiply with w by wd by a to find the time of the falling rate period. So, this is one approach. Now, when the rate is a linear function of x, that means the r, which is the drying rate during the falling rate period, will be equal to a x plus b. Okay. So, then dr, if we differentiate this, dr will be equal to a into dx, right. Then we can put this expression, that is instead of dx we can put this expression dr by a in this above equation. Okay. So, in this equation instead of dx we can put dr by a, then put the value of a for two different moisture content, and then we can derive the time. So, the process will be like this, since if it is a, if the drying rate in the falling rate zone is it is coming linear function, okay. So, if it is coming in a linear fashion, so then we can take any two segment as x1 and x2, okay, x1 and x2, where this point, the moment the falling rate start, that is xc, critical moisture content. Okay. So, in this case we can write this one, that R1 equal to Ax1 plus B, and R2 that is Ax2 plus B. Okay. So, from this we can calculate the value of A, right. So, this is R1 minus R2 by X1 minus X2. Okay. So, R will be equal to Rc into X1 minus Xe divided by Xe minus Xc, because R is the rate, R is the rate of the falling rate period. So, which is Rc, that is the constant rate period, into X1 minus Xe divided by Xc, that is the critical moisture content, minus Xe. So, in this case, if we here in this case, from the constant rate, when it stops, that means the at the critical moisture content, and to that for any moisture content if we consider, then we can calculate the value of R like this. So, finally, this Tf would be Wd by small a into A, because the dx we have replaced with dr by A. So, that is coming here. So, R2 integration R2 to R1 dr by R. So, Wd by A into small a ln R1 by R2 into Wd Xc minus Xc by A into Rc. So, the value of A, we have put here in this equation. So, we are getting Xc minus Xe divided by A into Rc, which is constant rate period, because here if we put the value of A, we are getting x1 minus x2 by R1 minus R2, and then if we consider this from the critical moisture content Xc to equilibrium moisture content Xe, then we can get this expression, right. So, this will be the expression of falling rate time period for drying mechanism, if we consider that the drying rate is proportional to the free moisture content, or it is a linear function of the free moisture content in this fashion, Ax plus B. Now, another case will be when the rate is a linear function through the origin, then R equal to Ax and dx equal to dr by A. So, in this case the slope will be represented as Rc divided by Xc. Okay. If it is goes by this, so this is our Xc, this is our R, and this is our X. So, at any moment the slope we can calculate as RC by XC at this point, right. So, TF, this is equal to WD by A, small a into capital A into R2 to R1 dr by R, that is equal to WD by AA into ln of R1 by R2. So, in the place of small a we will put RC by XC. So, we are getting this equation WD into XC, A into RC, ln of here RC by R2, that we have replaced with XC by X2. Okay. So, that we have put here. Now, next thing is that if we consider that the slope is not linear, if we plot the drying rate versus moisture content, so the slope is not, the line is not linear, in that case we can consider that this is because of the diffusion mechanism, right. So, for the diffusion mechanism, since the mass transfer is here, the governing function is the diffusion mechanism in the falling rate, and also the structure or shape of the material, because shrinkage has happened and the structure of the material will change. So, therefore, this drying rate in case of the falling rate period governed by the diffusion mechanism will be presented by Fick's second law of diffusion, which is the diffusion equation for the unsteady state diffusion. Okay. So, using that liquid diffusion of moisture in the falling rate, we can write the expression as x minus xc by xc minus xe. Okay. So, this is equal to 8 by pi square into e to the power dl, that is the diffusion coefficient, into T time into pi by 2x1 square. Okay. So, we generally take the first term only, there are other terms, but when we consider that long time diffusion mechanism, the first term will give us the reasonable accuracy in the calculation, and also we can consider that x e as 0. So, in that case simply we can express this in terms of x by x e. So, that has been done here in this equation, and the function t has been considered as the time required in the falling rate period, that is T f, that is equal to 4 into a square by pi square into dl into ln 8 x 1 star by pi square into x 2 star. So, here this a, small a, or if we write x 1, it is also you may get x 1 in some books. So, that is the characteristic dimension, and it is taken as the half thickness for the slab when drying occurs from both the sides, and if it is from one side only, we can take the thickness as the dimension a, and if it is a cylindrical object. So, most of the cases if we deal with the infinite cylinder, we can take the radius as the dimension, and for sphere also we can take the radius as the characteristic dimension. So, eventually we are getting that the time here will vary based on the free moisture available, that is x 1 by x c. So, x c, that is the critical moisture content, or here it is x 2 star, that will be fixed for a particular case. So, it will vary only with the free moisture, that is x minus x c, or here x 1 star that is available, and also it will vary with the diffusivity dl. Okay. And the characteristic dimension a, that will also be a significant parameter in this kind of falling rate calculation. Now, if you see one problem where the problem is such that mango slices were dried from 40% to 10% in 2 hours, the drying rate remained constant up to 15%. If the EMC is 2%, calculate the total time required to dry from 40% to 4%, and all moisture content are represented in dry basis. So, here two phases are rate period are involved, constant rate and falling rate. So, first we will have to see that what is the constant rate period here. So, it has been mentioned that 40% to 15%. So, 0.4 minus 0.15, this much has been removed. So, this into WD, that is weight of the dry matter divided by area into constant rate period RC. So, this will give the time for the constant rate drying, that is coming 0.25 into WD by A into RC. Okay. So, when time equal to 2 hours, so this 2 hours will combine the constant rate as well as the falling rate period. So, that is equal to 0.25 into WD by ARC plus WD by ARC into moisture content difference, that is EMC 0.15 to EMC 0.02 and critical is 0.15, okay, into ln of 0.15 minus 0.02 divided by 0.1 minus 0.02. Okay. So, so here we have to dry from 40% to 10% in 2 hours, right. So, 0.15 is the critical moisture content, 0.1 is the final to which we need to dry, 0.02 is the EMC. So, then what we can do is we need to find this factor, that is WD by A into RC, that is coming 6.3874. So, for the second case, what we need to find that T time, that is equal to Tc plus Tf, that is equal to 0.25 into WD by ARC plus WD into 0.15 minus 0.02 by ARC into ln of 0.15 minus 0.02 divided by 0.04 minus 0.02, because then we have to dry from 40% to 4%, not 10%, that was in the previous case. So, in this case, since we now know the value of WD by ARC, we will put it here and we can get that it is 3.15 hour. So, instead of 2 hour, if we need to further dry it from 10% to 4%, we need to extend this much time, 1.15 hour extra. So, we can see that as the falling rate time increase, because more moisture we need to evaporate in the falling rate zone, time requirement will be significantly higher, because the rate in the falling rate drying period will be very much less. Okay. We will stop now, we will continue in the next class. Thank you.